So for our first review question, I want to ask you this. If this is our chemical reaction between aluminum and oxygen to make aluminum oxide, how many grams of oxygen are going to be consumed, are going to react if we react 15 grams of aluminum? So just as a reminder from an organizational kind of standpoint, this is what we're looking at. Only difference here, we're going to put in grams of aluminum and grams of aluminum oxide as our points here. But the idea is the same. Grams of one to moles, use the balanced equation to convert the moles of one substance to another, use the molar mass to go the rest of the way. So we're looking for 3 conversion steps here. And if you don't have a copy of the periodic table handy, hopefully you've got one that you packed with you. Otherwise, we'll let you borrow one for now. Right, so organizationally, this is the kind of thing that we're looking to do. We need to turn the grams of aluminum into moles. We need to turn the moles of aluminum into moles of oxygen. We need to turn the moles of oxygen into grams. So each one of these arrows needs to be represented by a conversion. And if we've done our conversions properly, everything is canceling out except for the grams of oxygen, which is what we're trying to find, since that's what the question asked us for. So now it's just a matter of we got to put in the right values in the right places. So for this first conversion, we're looking for the molar mass of aluminum. 1 mole of aluminum is 26.98 grams. In the second conversion, we're going from moles of aluminum to oxygen. Remember, that's where we use these coefficients. 3 oxygens for 4 aluminums. And then finally, this is another molar mass conversion. 1 mole of oxygen is going to be 2 oxygens. So 16 each, 32.00 in total. I do the calculations. 15 times 3 times 32 divided by 26.98 divided by 4 to 2 significant figures, because we only started with 2 here initially. We're going to get 13 grams of oxygen. So again, the whole thing here is about a process. We've got to be able to systematically and procedurally go from one piece of information about one substance, and through the use of moles and the balanced equation, convert it into another piece of information about a different substance. Any questions with this particular example? Isaac?
use the wrong coefficient, but the same gram amount of thought.
Okay, what coefficients did you use?
I used the 3 and then 2 on the reactant side. And then instead of the 32 mole, I used 160. I don't know how I got the same.
Okay, so I think you kind of lucked into it, to be honest. So one thing that we have to remember is that we get certain samples that are going to be so oxygen, hydrogen, nitrogen, fluorine, chlorine, bromine, those diatomic substances, we have to remember that their molar masses are going to be the double of their atomic masses because they're molecular. So make sure that when we're doing this step here at the end, or even any step that involves a mass, make sure that we are doing what the formula says and not just looking at the periodic table. So seeing that it was O2 should have told you I needed to double the mass of the oxygen and get 32. And then for the coefficient part, make sure that you're lining up the correct coefficients there, because there are going to be differences there, and that could be the difference between being correct and being incorrect. Other questions? All right, let's do another one here. Slightly different kind of calculation in terms of the end goal, but overall same idea. How many moles of carbon dioxide are produced when 8.75 milliliters of methanol react completely with oxygen? The density of the methanol is 0.79 grams per milliliter. So this one is slightly different because we are not starting with a mass of methanol, but rather a volume. Now, volume's not explicitly on that map that I showed you, but we should know from our first unit, module number 1, that we can use density to interconvert between mass and volume for a given substance. And so that's going to be the first step in our process. We want to take the milliliters of methanol and turn them into grams. Then we're going to turn the grams of methanol into moles and convert the moles of methanol into moles of carbon dioxide. And since that is what we're asked for, that's where we will stop this particular calculation. So there are a number of ways to do this first conversion. You can use the algebraic method. So you can say, okay, well, density is mass over volume. And so I could set up an equation, 0.79 is equal to x over 8.75 and solve for x. Perfectly reasonable way to get the mass. However, we also taught you in module 1 that this kind of value is a ready-made conversion factor because we've got 0.79 grams divided by 1 milliliter. And so I could use that as my converting factor instead. So starting with the 8.75 milliliters of methanol, 1 milliliter is equal to 0.79 grams. My milliliters cancel. I'm left with grams. Now all that's left for me to do is turn those grams of methanol into moles. And then those moles of methanol into moles of carbon dioxide. So I'm going to give you a couple of minutes to do that here yourselves and see if you can come up with the correct answer. Then we'll go through it together. All right, so you should be looking at this as far as kind of how everything needs to fill in. So for the molar mass of methanol is 32.05. How did I get that? I had to add together the molar mass of carbon, of oxygen, and of 4 hydrogens in total. So carbon's 12.01, oxygen 16, each hydrogen is 1.01. That's how I get the 32.05. The last one comes from the balanced equation itself. So I had a coefficient of 2 for the methanol, a coefficient of 2 for the carbon dioxide. That's where the 2's come from in that particular fraction. Now, one really important note here, things that can save you a little bit of time. If you notice that you've got a conversion that has the same numerator and the same denominator, you can mark that out because they're going to cancel each other out. So instead of multiplying by 2 and then dividing by 2, I'm just going to ignore the numbers there. And if I do that, simplifies it a little bit for me, 8.75 times 0.79 divided by 32.05, I'm looking at 0.22 moles of carbon dioxide. Now, 2 significant figures there coming from the fact that there are only 2 in that density that they gave us. Everything else kind of seems to work out okay. All right, any questions with this example before we move on to limiting reactants? All right, so Wednesday, we started to kind of scratch on this idea of the limiting reactant. Let's do a little bit more concrete looking at it. So a limiting reactant is a reactant that ultimately limits how much product is made. And it's done so because in that process, the limiting reactant is completely consumed. It's all used up. Any reactant that does not get fully used up is considered to be in excess. Excess reactants. Reactants that after the reaction is over, there is still stuff left over. So if we come back to this example that we started with stoichiometry, the idea of s'mores, well, if I have 16 graham crackers and 18 chocolates and 2 marshmallows, I can only make 2 s'mores out of those ingredients. As soon as I use up the marshmallows, doesn't matter how much graham cracker and chocolate I have, the end result is that I don't have the marshmallows, so I don't have a s'more. In that example, marshmallow is the limiting reactant. It's the thing that runs out. The other things, the graham crackers and chocolate, those are in excess. Those are left over. Let's take a look at another kind of idea here. What is the maximum number of s'mores that I can make if this is my ingredient list? Now, just remember, again, our formula, if you will, 2 graham crackers plus 3 chocolate and 1 marshmallow make a s'more. If this is what I have, how many of those final products can I make? So I'm looking for a number here. Now, the correct answer to this problem is 8. How do I get to that correct answer? Well, the easiest way to go about it is to look at each one of those ingredients and figure out how many s'mores can I make with that if that was the only thing that I had to use. And so if I look at the graham crackers, 35 divided by 2 would give me 17 and a half. And since there's no such thing as half of a s'more, I could only make 17 s'mores off of those graham crackers. For the chocolates, I need 3 chocolates per s'more, so that's going to get me 8. And for the marshmallow, I only need 1, so I can make 50 s'mores off the number of marshmallows that I have. Why is the answer 8? Well, after that 8th s'more, there's no more chocolate left. So even though I have graham crackers and I have marshmallows, and on their own, they are great snacks, I don't have everything I need to make a s'more anymore. Now, I give you this as an example because when we look at things from a more chemically focused kind of perspective, this very same idea is going to pull through here again. When we're given multiple amounts of reactants and trying to figure out which one is going to drive the amount of product, we can use a process very similar to this to get us to what will ultimately be the correct answer. So if I were given a question like this, where I've got a reaction, aluminum is reacting with chlorine to make aluminum chloride. If I am told how much aluminum I have and how much chlorine I have, the answer to figuring out the question, what is the limiting reactant, comes down to me being able to discern in some kind of way which one of these is going to run out first. Now, the easiest way to do that is exactly the way that we did it with the s'mores problem. The easiest way of going about this is figure out how much product can I get from the aluminum, how much product can I get from the chlorine, and which one is going to run out first. So we're going to put in some new terms as we do this, but let's think out the process here. I'm going to start with grams of a reactant. That reactant can either be aluminum or chlorine. And where I want to end is I want to end with some amount of product. And since there's only one product here, I'm going to turn it into aluminum chloride. Now, depending upon what I was asked to do after this, I could go a number of different directions. But the reality of the situation is I need to be able to compare the aluminum with the chlorine on a level playing field. And the only way to get them on a level playing field is to convert them to a substance that is different from themselves so that I can compare each of them directly to each other. So if I just turn the grams into moles, yes, the unit is the same, but moles of aluminum versus moles of chlorine is not a comparison. They're different substances. As you can see in the reaction, they react in different rates. The chlorine is going to react 1.5 times faster than the aluminum is because the ratio there is 3:2. So I need to put them on a level playing field, which means I'm going to convert both of them into one of the products. And since there's only one product here, we're going to choose aluminum chloride because we have no other option. Now, to get a level playing field, I only need to go to moles. I can go to grams if I want. And in some cases, it'll make sense to do so. If I'm trying to figure out how many grams of aluminum chloride are made in this process, yeah, throw on that extra step so that I have the conversion that I need. But if I'm just trying to compare, if I'm just trying to figure out which one's going to run out first, I can stop at moles. Because, again, I'm just trying to get them to a place where I can compare them directly. And to compare them directly, I have to have them both in the same unit, and they have to be talking about the same substance. So in this process, we're going to take our grams of aluminum, so 0.362 grams of aluminum. First thing that we're going to do, turn that grams of aluminum into moles. And then the next thing we're going to do, take that moles of aluminum and turn it into moles of aluminum chloride. Now, first step, molar mass step, 1 mole of aluminum is 26.98 grams. Got that directly off of the periodic table. So grams of aluminum cancel. For the second step, moles of aluminum to aluminum chloride, pulling these directly off of the balanced chemical equation, it's a 2-to-2 ratio. 2 aluminum chlorides, 2 aluminums. So in addition to canceling the units, I can also cancel the numbers here because they are the same. And so from the calculation standpoint, 0.362 divided by 26.98 to 3 significant figures, 0.0134 moles of aluminum chloride. So I've got half of it done. I have to do the other half. I have to see if the chlorine matches it or comes in over it or under it so I can determine which one is going to run out. Process, pretty much the same. Start with my amount of chlorine. I'm going to turn the grams of chlorine into moles. And the moles of chlorine into moles of aluminum chloride. For the molar mass, 1 mole of chlorine. Chlorine is 35.45, but there are 2 of them, so I need to multiply by 2, 70.90. Grams of chlorine cancel. Now for the mole conversion, I'm comparing chlorine to aluminum chloride, 2 aluminum chloride for 3 chlorine. The moles of chlorine cancel. The numbers do not this time. 0.945 times 2 divided by 70.90 divided by 3. 0.00889 moles of aluminum chloride. So what does this tell us? Okay, I've got them both on even terms now, so I can compare them directly. Which one made less, the chlorine or the aluminum? The chlorine. Chlorine made less. So what that tells us is this didn't happen. Aluminum is in excess. This did happen. And it happened because chlorine is the limiting reactant. Charles? Yes, you have to go by the lowest because once this amount has been made, there's no more chlorine to make anymore. So we always have to go by the lowest when we do these kinds of problems. Now, in addition to this, we can get something called the theoretical yield. Now, theoretical yield will come up again when we talk about percent yields, but the idea here is relatively simple. This amount is the amount of aluminum chloride that we would expect from this reaction. That's the value in moles. If I wanted to take it into grams, all I would need to do is multiply it by its molar mass. And so for that, 26.98 plus 3 times 35.45, 133.33. Would give me 1.19 grams of aluminum chloride. So I could take theoretical yield. If I just need moles, that's a perfectly good way of expressing theoretical yield, is in moles. If I need grams, I can take that moles, turn it into grams by multiplying by the molar mass. Now I have a theoretical yield in grams instead. The ideas don't really change. We just manipulate the units based upon what we need. But when we do limiting reactant problems like this is the way that we want to compare them. We want to look at them in this kind of way. Take what we're given, get them to where we can fairly compare the amounts, and choose the lowest. The lowest tells us that that reactant is the limiting reactant, and that what we got from that calculation is the yield, what we would expect from the reaction. Any questions here? All right, let's try a couple here. Now, these are simpler examples. Examples like the one that we just did, you'll see a lot of in the homework assignment tonight. Let's see if we have the concept before we get into anything deeper. So I've got 9 moles of nitrogen and 9 moles of hydrogen. How many moles of ammonia can be formed here? So again, looking for a number here. All that you have to do this time, this is a very simple conversion. We're just going from moles of reactant to moles of ammonia. So when you have an answer, go ahead and put it in. For the nitrogen, we're starting with 9 moles. The conversion here, 2 ammonia for every 1 nitrogen. So 9 times 2 would give me 18 moles of ammonia. For the hydrogen, 2 ammonia for every 3 hydrogen. So my moles of hydrogen cancel. 18 divided by 3 would give me 6 moles of ammonia. And so what that should tell me is that this is not going to happen. This did. So nitrogen is in excess. Hydrogen is the limiting reactant, and the theoretical yield in this case would be 6 moles of ammonia. So when we do limiting reactant kinds of calculations, there is just a wealth of information that we can pull out of the results of those problems. All right, any questions with this one? All right, I'm gonna ask you to try a similar one. I've got 0.25 moles of A2 and 0.33 moles of B2. How many moles of AB should I expect from this reaction if that is the balanced equation? Formatting wise, very, very similar. We're going from moles of reactant to moles of AB. So you just need to set it up and figure out which one runs out. So if I set it up correctly and do my math out, A2 will generate half of a mole of product. B2 will generate 2/3 of a mole of AB. So again, we go down to the lowest. Lowest value means that this one didn't happen, this one did. And so from this, we can conclude A2 is the limiting reactant. It's the one that gave us the least amount of product. B2 is in excess because it gave us too much. And the theoretical yield would be half of a mole of the product AB. Now, the reason I keep mentioning this idea of theoretical yields is because when we start to actually take this out of calculation land and into practice, there are going to be some instances where we want to evaluate efficiency of our processes. So theoretical yield is the amount of product that we would expect from ideal conditions. Another way of putting this would be through calculations or stoichiometry. But you know as well as I do that when we actually get into practice in a laboratory situation, we may not actually get what we're supposed to. Sometimes we make mistakes, we end up getting more than we're supposed to. Usually that means that we've made some kind of mistake in the procedure. Sometimes things just happen, we end up getting less than we're supposed to. So how do we actually evaluate efficiency there? Well, we do it with something called percent yield. Percent yield takes what we did in the experiment and compares it to what we should have gotten from stoichiometry. So actual yield divided by theoretical yield times 100% to turn this fraction into a percentage. Just looking at a couple of examples of this in action. So coming back to the s'mores. Let's say that we had enough ingredients that we could make 12 s'mores. But because things happen, we end up burning some of the marshmallows, they fell off our roasting sticks, whatever. We only ended up making 11. The percent yield of that process would have been taking the actual yield, the 11 that we made, and dividing it by the 12 that we should have made, and multiplying it by 100%. So 11 over 12 times 100%, we would get 91.67%. So we got just a little bit less than 92% of the s'mores we were supposed to. Now that translates into the chemical world as well. Remember this problem? We just did it about 10 minutes ago. In that problem, we determined that the theoretical yield was 1.19 grams. And if you don't believe me, we can go back and look. That was the number we came up with at the end there. To figure out the percent yield, we have to take this. This is what we actually got in the reaction and compare it. So percent yield is 0.420 grams divided by 1.19 grams times 100%. And if we do that calculation out, 0.42 divided by 1.19, to 3 digits, 3 significant figures, we get 35.3%, which is not terribly great, but in context, it's not terribly bad either. A lot of times these reactions just happen so slowly that at some point we have to go, you know what, let's just call it a day. And we don't get everything that we're supposed to. So percent yield calculations piggyback off of stoichiometry kinds of problems. This is a very common kind of example where you have to do a limiting reactant thing first. It's also entirely possible that you don't have to do the limiting reactant thing. You just have to do the stoichiometry thing to figure out the theoretical yield first. So that will get explored in that assignment that's due this evening. If you have any questions between now and then, feel free to shoot me an email, send me a text message or a direct message through Blackboard. And I will see you on Wednesday for our next proficiency as well as the start of Module 5.